Today is a big day. Well, this video is a big deal. We are going to talk about Grignard reagents, one of the most useful reactions of organic chemistry. Let's get into it. So we are in Key Concepts, Unit 1, Part 4. I thought I could cover Part 4 in 2 videos, and I realized it might make more sense to do 3. So we're going to cover synthesis of esters and Grignard reagents in this video, and then we will finish Part 4 of Key Concepts in a final video for Unit 1. So if you have, let's see, am I all set up here? Yes. If you have your key concepts, you can take them out, mark them up, make some notes, whatever you do to help you remember this information. Here you go. So if you scroll down the key concepts, reaction set number 3, I don't know. We are looking at synthesis of esters. These are important too. I don't want to say that this is not important. It is important. Grignard's just, however, just more common, more useful. But esters are important functional groups, and one very useful way to make them is to take an alcohol or a carboxylic acid. Here we go. Reagents, alcohol, carboxylic acid, and then you need an acid catalyst. And again, the acid catalyst may show up over the arrow in multiple different forms. Just get ready for some source of H+. Acids are required. So what do I want to do? Let's just do nail polish remover, the non-acetone type. This is carboxylic acid. There's a methyl group over here, 2 carbons total. This is actually acetic acid. It's the active component of vinegar. Very, very common. Take some alcohol, the kind found in beer and wine, ethanol, 2 carbons, an alcohol group. There we go. So now I have an alcohol. I got my carboxylic acid. And then let's use an acid catalyst. And you get to decide how you want to write that chemical formula, whatever, signify there is an acid present. Sometimes you'll see a little cat, H+, meaning, oh, it's a catalytic amount. Not so important. Just need some source of H+. And then this is kind of cool. I had some students show me this little trick. What you do is you face, when you draw your structures, you face the alcohol groups towards each other. That's a carboxylic acid, but it's got an OH group. So the OH groups face each other, and then you remove a water molecule between them. So you decide which oxygen to grab, but grab both H's. And that becomes water. And that actually is one of your products. But in organic chemistry, we really only track the carbon atoms, and the organic chemist is not so interested in this water molecule because it doesn't have any carbon. And then to make the ester, you just link the 2 pieces together, the parts that are not water. So we got this 2 carbons and a double bond O from the carboxylic acid, and then the oxygen comes from the alcohol, and the oxygen keeps its carbons. It's got 2 carbons there. And then this is ethyl acetate, non-acetone nail polish remover. Yay, it's an ester. What else do we need to know about this? There will be a mechanism to memorize, but you know what? Let's wait until we talk about carboxylic acids as a functional group, and we'll deal with all the mechanisms of carboxylic acids then. And thankfully, it's a pretty common mechanism. There's not a lot of them. It just makes more sense to procrastinate, to put it off until Unit 3. So you don't have to know it now. You just need to know how to make an ester. You need to know the reagents. And you need to know how to predict the correct structure, right? So part of the ester comes from the carboxylic acid. The other part comes from the alcohol. What else do you need to know? It's also an equilibrium reaction. So technically, we should have a double arrow here. And you can reverse or hydrolyze the ester back to the carboxylic acid and the alcohol by adding water and acid catalyst. And Le principle says if you add more water, you'll drive the reaction to the side that gets rid of the extra water. It drives it to the left, and it'll help hydrolyze it. This is actually a reaction found in our bodies. This is one way that we metabolize fats to get fatty acids, carboxylic acids, and glycerol. Anyways, getting off track, just saying it's important. And then our bodies will actually take those fatty acids and glycerol and recombine them to make new fats, depending on the needs of your body. What else needs to be said about this? Nothing. We're done. More on esters and the synthesis of esters in Unit 3. Oh, I remember. There was one more thing. If you need to make an ester on the exam, can we do this yet? That might be too far. Let's not make it so. Try to think. I don't want this video to be too long. But here, let's should do a little more planning. Let's say we want to make this ester during the exam, during a synthesis problem. And you have to use 4 carbons or fewer, 4 carbon alcohols or fewer. Okay, so how would you make this ester? Well, retrosynthetic analysis is the best strategy. So think about going backwards, like think about, well, what's your final step to make the product, the ester? It's this one. To synthesize an ester, you need a carboxylic acid and an alcohol. So kind of think backwards on the one we did. This piece of the ester came from the alcohol. So let's do the same thing. This piece came from the alcohol. And it's an alcohol, so put the hydrogen on it. So these are the atoms of the ester that came from the alcohol. And then you need a carboxylic acid. Well, that's the other side, right? So what's not dashed in here is 2 carbons and double bond O. Yeah, the 2 carbons double bond O came from the carboxylic acid. So now in our molecule, we have 3 carbons. And then make it a carboxylic acid. I know, it's pretty ugly. What's wrong with my hand? Steady, please. Okay, we got a carboxylic acid, the alcohol, and don't forget the acid catalyst. It's worth a point or half a point on the exam. Details are important. Cool. Okay, now for a synthesis, multi-step synthesis problems on the exams, you must begin with 4 carbon alcohols or acetylene, right? The simplest alkyne. What else? Oh, you can also start with benzene. You don't have to make benzene. I think that's everything you can start with. So what have we got? We got 4 carbon alcohol right here. So this is good. This is legal. We do not have to make this. Yay. Got a lot of points now, just this last step, because this is one of the legal starting materials. This one, however, is not. Can't start with the carboxylic acid. These are the only molecules you can do. It has 3 carbons. So is it possible to create it from an alcohol with 3 carbons? The answer is yes. Check out the last video, and you can use a strong oxidizer on a primary alcohol. KMNO4 is the most popular one, most environmentally friendly, but you could use one of the other strong oxidizers. You don't have to list them all, but I will just as a review. Dichromate in either the potassium or the sodium salt form. There you go. And that's multi-step synthesis for making an ester. Anything else I need to talk about? No, we're good. Cool. On to the show. The big boy, Grignard Reagents and Grignard Reactions. Oh, before we get there, quick little review. As you go through your key concepts, I like these because it helps me remember all the details. We're moving on to the last part of key concept, Unit 1, Part 4, where we're talking about how to make alcohols, the synthesis of alcohols. And you still need to know those old reactions. The most important one is the SN2 reaction of an alkyl halide. So here's an alkyl halide. with hydroxide ion, maybe it'd be sodium hydroxide, maybe potassium hydroxide. You must use a polar product solvent because we have a strong base. And strong base, primary or secondary halide, can do an E2 reaction, and to help limit that from happening, let's add a product solvent. They said, yeah, polar product solvent, DMSO, DMF, acetone, or acetonitrile are good choices. And then we do an SN2 reaction. Nice, quick mechanism, 2 arrows, lone pair on the good nucleophile strong base, can attack the carbon because the bromine's slightly negative, carbon's slightly positive, opposite charge attract, right? Bromine's more electronegative than carbon, creating that polar covalent bond, drawing in the oxygen, strike here, and carbon can't make more than 4 bonds. So when the new bond is formed, an old bond breaks, and that's bromine. Bromine takes off, and we make our alcohol. Yay! So that is one of the most important reactions to make or synthesize an alcohol. There's also some alkene reactions. So I think I reviewed those in a previous video. So take a look at those, review those. They could be useful to you on exams if you need to make an alcohol from an alkene. Cool. All right, new reaction. Here we go. Grignard reactions, Grignard reagents. And we got a disclaimer here, a warning. Grignards are powerful bases. Okay, and if there's any hydrogen atoms that can act as an acid towards these extremely powerful bases, that's what will happen. Acid-base reactions are so much faster than most other types of reactions, they win the race. And that's something you have to watch out for. It's not something that's going to be told, oh, predict the acid-base reaction of this Grignard reaction. No, you just have to be on the lookout for it. So it's really important to have a firm understanding of order basicity. What makes something acidic? What makes it basic? And I got an individual standalone video titled Order Basicity for you to look at and get a good feel what makes an acid, what makes a base. Okay, so that's the disclaimer. As you look at a reaction and we say, ooh, I'll tell you how to identify as a Grignard. You say, ooh, it's a Grignard. Wait. Let's make sure the Grignard's not going to do an acid-base reaction. Cool. And this is how I like doing it. If we can go face-to-face and into the chemistry lab, we will do a Grignard reaction. And what we have to do is be extremely careful to use dry glassware. All the pipettes have to be free of water. You do not breathe on it. That's not an exaggeration. You're moist. There's moisture in your breath. And it's like very much so like water. Just watching. Once it react. Because water is a weak acid, but towards a very powerful Grignard reagent, it's a very efficient acid because Grignard reagents are just so darn powerful. Strong bases. One of the most powerful bases we know of. Okay. Enough warning. Get on to the good stuff. Okay, the good stuff is if you can make a Grignard in the absence of water or any other acid, then they can react with aldehydes, ketones, and esters. Aldehydes, ketones, and esters. And the commonality here, common feature, is they all have carbon-oxygen double bonds. Yep, and so they have a very common mechanism. The Grignard is going to have a little longer mechanism because of the second oxygen, but mechanisms are very similar. Cool. You need to know those. Again, Grignard reactions, just one of the most popular ones, most useful ones in organic chemistry. So yeah, we need to know how they work. We need them step-by-step mechanisms. Let's talk about how to prepare a reagent so you can do a Grignard reaction. Yeah, that's next. Okay. So first we have to make the Grignard reagent. the component that we need for a Grignard reaction. What you do is you take an alkyl halide. My favorite halide is bromine. The halide can be primary, secondary, or tertiary. It can be chlorine, fluorine. It cannot be fluorine. Chlorine, bromine, or iodide, not fluorine. Remember we talked about fluorine is found in Teflon. Nothing sticks to Teflon. Fluorine is just weird. The real reason is carbon-fluorine makes a very strong bond. And the reagent just doesn't form. The carbon-fluorine bond survives. Nice thing about Grignard reagents is that you don't have to have alkanes with halides. You can also have aryl halides. Aryl referring to the arene or the aromatic functional group. So you can have a benzene ring with your favorite halide on, chlorine, bromine, or iodide. You can also use vinyl halides. So you can have a couple double bonds or one double bond, whatever, and put your favorite halide attached to that sp2. This is also sp2 hybridized carbon. Still works. Very versatile. And again, that actually adds to its popularity as a good reagent because it's so versatile, so many options. Chemists love options. Okay, I think I got all those options. Let's double check my list. List. Yeah, we're good. Okay, how do you make the Grignard reagent? Magnesium is the key. And what you do is in the lab, you use elemental or solid magnesium metal. It's kind of cool. Magnesium metal is actually quite soft, very stable. Slow. Well, there's a slight oxide coating, so it tarnishes, if you will. Sometimes what we do in the lab, we'll take a little steel wool, polish it up, and then we'll cut little pieces of the magnesium with scissors. Yeah, it's that soft. You can just cut it in pieces, and you weigh out the pieces. You avoid touching them because there's moisture on your hands and water sneaking in the back like, can I come in? No, stay out, water. So take the magnesium metal, mix it in with the alkyl halide, and then sometimes you have to get in there and scratch the metal because even after you polish it, there's oxygen in the air and immediately can start reoxidizing the surface and changing the surface metal to an oxide, which is ionic and doesn't react. Anyways, there's a little induction period, it's called, where it's slow to start going, but then it takes off. And the magnesium metal starts to bubble. It actually doesn't bubble. It doesn't create a gas unless you have water around. Darn it. It will start heating up the solvent. And the solvent is usually ether, diethyl ether, which boils really low temperature, around 40 degrees, I believe, Celsius. And your body temperature is 37 degrees Celsius. So that gives you a feel how low a boiling point it is. It's an exothermic reaction, so it heats up the solvent. You see it start boiling. Kind of cool. It actually has some pretty cool colors. So you take this clear alkyl halide, usually has no color, magnesium metal, shiny piece of metal, and then all of a sudden the liquid starts boiling, starts changing colors. The metal dissolves, disappears, and that's what you gotta wait for. You gotta wait for all the metal to dissolve. That's the indication that you have formed a Grignard. So what is the Grignard reagent? It simply inserts itself between the carbon and the halide, which is kind of interesting in terms from the polarity of this bond. If you take an alkyl halide, halides are more electronegative than carbon. So bromine takes on a slight negative charge, carbon takes on a slight positive charge. Magnesium will actually insert itself between the carbon and the halide. And we usually write the Grignard reagent like this. And now, what is the polarity of this covalent bond between carbon and magnesium? Well, magnesium is an alkaline earth metal. It's on the far left of the periodic table. Carbon is a nonmetal on the right. So carbon is more electronegative than magnesium. So now carbon bears a slight negative charge. So you feel like, oh, it's a polarity shift. It went from slight positive, slight negative. Yeah, what's the big deal? if we draw the resonance structures, we get a better sense of the big deal of the reagent, the Grignard reagent we just made. This carbon can actually be so electronegative, if you will, compared to magnesium. It can pull these bonding electrons and form a lone pair. Ooh, that's not so nice. Carbon is not very electronegative compared to fluorine and oxygen, right? So it doesn't stabilize its negative charge very well. That's what makes it a very strong base. And then what becomes of the magnesium, the bromine? Well, the magnesium bromide bond is ionic. Magnesium has a -1 charge here, bromine has a plus, the other way. Magnesium has a +1 charge, bromine has a -1 charge. But you are more familiar with alkaline earth metals taking on a +2 charge. Yeah, and so if you put a -1 charge on the carbon, bromine has a -1, magnesium balances it with a +2. Experimental evidence, though, suggests that this is not the correct structure, because if it was ionic, it shouldn't dissolve in nonpolar solvents. And diethyl ether is fairly nonpolar, and the Grignard reagents actually do dissolve in diethyl ether, suggesting that the bond between carbon and magnesium is more of a covalent bond than an ionic bond. All right, I got enough of this. Because it's so basic, carbon doesn't like that negative charge, it's going to be extremely reactive. So if you prepare the Grignard reagent and let it sit, this guy, water will get in the reaction somehow. If you have a stopper in place, air will kind of leak through. You know, you open up, how you doing, Grignard? You talk to it, you breathe on it, you have moisture, there's moisture in your breath. This the carbon will grab H+ off of water so that the carbon can go back to having 4 bonds, 4 covalent bonds, and no charge. So soon after preparing the Grignard, which is right over here, you have to react it with whichever compound you want. Do you want to use an aldehyde? And there's 2 choices. Do you want to use a ketone, or do you want to use an ester? All right, I found this nice graphic on the internet, and I thought, cool, I don't have to type all this stuff. But it's formatted in a way I'm not usually accustomed to. So let's break this down, see what's going on here. Okay, on the far left, we have the Grignard reagent, and you know that because there's the Mg. My Grignard reagent I just wrote up above was this one. So whoever made this graphic, their favorite halo was chlorine. Mine's bromine. Big deal, still a Grignard reagent, just as powerful because the reactivity is right here on this carbon. They also did a little shortcut, which is actually quite common in organic chemistry. They used the letter R. If you go to the periodic table, there is no element R. This is just an abbreviation for the rest or the remainder of the molecule. So my R group is a propyl group, right? There's 3 carbons here. That's the R group. And so if you see R dash some functional group, R can be anything, pretty much. We'll talk about some limitations shortly in this video. Okay, that explains this. So you can use any Grignard reagent to get any one of these 4 reactions to go. Okay, I hope that kind of impresses you. Well, it impresses you. Organic chemist says, ooh, that's a lot of choices. I can make a lot of different molecules. Yeah, and if you're in a pharmaceutical company trying to develop a new anti-cancer drug and you need to make some variety of molecules, Grignard reagents give you access to a variety of molecules. So again, variety of things. Alkyl chains and branch chains and rings, benzene rings with halides, double carbon-carbon double bonds with halides, lots of variety. That's just on the Grignard reagent side. On the carbonyl side, carbonyl, if we talked about that, maybe not formally, let's just throw it in here. Carbonyl is the nickname for the C double bond O group. So all functional groups that have a C double bond O, carbon-oxygen double bond, they can be called carbonyls. An aldehyde is a carbonyl. Yeah, I see the C double bond O. aldehyde, I just said that, ketone, carboxylic acids, esters, amides, anhydrides, acid chlorides. Anybody with C double bond O, you can refer to them as a carbonyl. However, typically when you hear carbonyl group, we usually think just aldehydes and ketones. Again, it's a nickname. The actual definition is a little vague. I try to avoid using that for that reason. It's not very precise. Done talking about carbonyls. Okay, let's get on with the Grignard reaction. Okay, so your Grignard reagent, whatever group, is going to be attached to magnesium and some halide. The carbon that is attached to the magnesium is the point of connection to the carbon that's double bonded to oxygen. So that's the common pattern for all four of these reactions. The R group and the C of the C double bond O form a single covalent bond after the Grignard reaction takes place. So this R connects to this C. That's what happened. R connected to that C. The C had two H's, still has those H's. The O is over here. Now, why is there a hydrogen here? Well, because oxygen prefers two bonds, right? This carbon that's got all four of its bonds. We bring in an R group to make a fourth single bond here. So the oxygen has to let go of the pi bond. And now the oxygen is negatively charged. We'll see this in the mechanism. And we have to add an acid to create, hey, an alcohol. So Grignard reagents, Grignard reactions produce alcohols. That's a common pattern. So let's just look at predicting products. If you have an aldehyde or formaldehyde is the specific aldehyde with two H's on either side of the carbonyl, the C double bond O group. An aldehyde is going to have some other remaining molecule. Sometimes what you'll see is a little prime, a little dash, hyphen, whatever, that's not hyphen, apostrophe. And that'll indicate that this R group, this remainder, can be different from the other one, or it could be the same. But I'm going to choose, hey, this R, I'll put it on the left side here. That comes from the Grignard, and then the remaining carbons, this R group and that C, came from the aldehyde. Ketone, doesn't really matter. Let's make this a prime and a double prime, and I'll call this a prime and a double prime. So in your ketone, ketone has a carbon double bond O. Ketone has a carbon on the left and right side of the ketone. So this R, the remaining half, I'm going to put up top. The remaining other half of the ketone, it's going to be right here. And the new R group that comes from the Grignard is right there. And finally, the ester. We'll go through the mechanism, but what happens is in the first step, you get one R group adding on to the carbon, and it kicks out the single bonded oxygen with this other group. Ooh, they actually use a prime group saying, hey, these R's can be different. And that's released, that's kicked out. H plus will be added to this negatively charged oxygen to make an alcohol over here. And then on this side, you can actually attack it a second time with a Grignard. So you're going to get two R groups. So let's circle two of these. If you wanted to balance the equation, which organic chemists usually don't do unless they're in the lab, you could put a 2 here if you want to show how it's balanced. You need 2 Grignard reagents for every 1 ester. And then this R group, let's make it a double prime because the ester over here has a prime on this alcohol group. Let's see, what else we need to know? Oh, we're highlighting importance here. If you want to take the Grignard reaction from the point of view of what are you going to make, you can choose a primary alcohol as your product, a secondary alcohol, or a tertiary one. And the tertiary can be made 2 ways. If you want a primary alcohol, start with formaldehyde. Technically what it does is it takes your Grignard and adds on 1 carbon. So this 1 carbon was added, and that carbon actually have an alcohol at the end of the chain. So if you want a primary alcohol, use formaldehyde with your Grignard reagent. But if you want a secondary alcohol, you must use a different aldehyde. And what it does is it takes the aldehyde's remaining carbons and that pseudo-bond carbon. Whoops, wrong one circle. There's the aldehyde carbon. And then we bring in the Grignard reagents carbons and connect them there, and then we get a secondary alcohol. Ketone is already going to have two sources of carbon, so this carbon's already secondary. We're going to bring in a third carbon and link it there to make it tertiary. Yeah, so the Grignard is bringing another group of carbons that's going to increase the classification of that carbon, if you will. So this carbon you would say is primary, it's only linked to one carbon. This carbon is linked to two, it's secondary. Is this a zero order carbon? I don't know what you call it. It has no carbons attached. But after Grignard attacks, now it's primary. Right, this carbon is now primary. Anyways, primary, secondary, tertiary alcohols, formaldehyde, aldehyde, ketone. Cool. And then if you want the same R group from the Grignard adding twice, start with an ester. You get the same group twice. Most students, most teachers do. I would start with a ketone. It's easier to see, shorter mechanism, and you can still get your tertiary alcohol. And if you want the two R groups to be the same, we'll start with a ketone that has two R groups the same. And then we bring in a different Grignard structure, whatever. Lots of variety. Cool. All righty, let's see. I think we got limitations down here, but we haven't seen the mechanism yet. So let's do it a couple times. Let's start with the easier one, aldehydes and ketones. So I'm going to start with this Grignard, and I'm going to add, let's start with benzaldehyde. Why not? So you can put the hydrogen here if you want to show the hydrogen of the aldehyde group. Don't have to, your choice. Oh, if you have an Mg, you must have acid. They go hand in hand. So the Grignard is a powerful base. Need to exclude water during the reaction, otherwise the Grignard will attack the water. Keep the water away, so now the Grignard can only attack this carbon because of the polarity of the oxygen being more electronegative. After the reaction's over, the Grignard part, you still have some remaining intermediates that are very basic, and you have to neutralize them with acid. So every Grignard reaction is going to have H3O plus or H plus, some source of acid afterwards. Half point or a point on the exam for getting that. So you earn points for writing in second reaction, not the same time, right? No acid during the Grignard reaction because the Grignard will attack the acid. So that's what the 2 means. Step 1, Grignard reaction. Step 2, later, after Grignard finishes, have the acid there to clean things up. Let's see the mechanism, and along the way we'll predict the products. It's a optional step, but I like to draw the resonance structure. Again, it's optional. So option 1 is draw the resonance structure. Now you have some lone pairs. Start your curved arrow here. Hey, negative charge. See anything you like over there? Oh yeah, I like that carbon. So let's connect to that. Let's make a bond. But carbon can't make 5 bonds. So as a new bond, this lone pair is creating a new bond between the propane group and the carbonyl carbon. The pi bond moves up onto oxygen. Besides, oxygen's yanking on these polar covalent bonds, trying to pull those electrons up to it. So carbon says, yeah, here you go. Here are the pi electrons because I got another source of electrons coming in. And what's cool, that's the end of the first reaction of the Grignard reaction. Very short mechanism. Yay. So the oxygen becomes negatively charged. We connect, we connect 1, 2, 3 carbons, and we connect it here where the magnesium used to be. So the magnesium used to be here, so I got 1, 2, 3. And when you're drawing it, you can draw it however you want. If you want to, have the zigzag down, whatever. Cool. That's enough for full credit on the first half of the mechanism. Some students are like, wait, where'd the magnesium bromine go? Well, the magnesium and bromine are not going to hang out with this carbon anymore because this carbon is neutral and magnesium has a +2 charge. So positive thing, what are you attracted to in this molecule? Oh yeah, this negative electron, sorry, this negative oxygen. So the magnesium is actually up here. We're done. We're not done with the whole mechanism, but hey, someone else might say, well, what's another way to draw the mechanism? Well, let's say this is how the reaction appeared on the exam. It's the same exact reaction. I flip the aldehyde around. So whoever's drawing it gets to decide. Reaction number 1, aldehyde reacts with the Grignard. Reaction number 2, throw an acid into the product mixture. And you can say, oh yeah, Dennis, here's the mechanism. These electrons that are actually the lone pair, this covalent bond, those electrons are actually going to bump up the pi bond. And then after the first reaction's over, oh wait, try again. Well, let's keep the orientation of that benzene ring the same way. Put the negative oxygen here and the benzene ring on the right. And then now the point connection's here. And I want to bring in these 3 carbons, 1, 2, 3, 1, 2, 3. So this carbon was from the Grignard, and then you link them together. There we go. And then this molecule is the same as that one. And again, on the exam, if you forget the MGBR, I'm cool with that. There's no carbons there. Someone else might say, no, I'll put it in there. Whatever. Okay, what about the water? Second step, again, we're trying to detail the full mechanism. Well, opposites attract. The oxygen is negative, the hydrogen is positive, hydronium is positive, and so a lone pair on that oxygen goes and grabs H+. The last step is an acid-base reaction. Add the acid to quench this base. It's a weird looking base, but just think of it just like sodium hydroxide, right? Draw the charges, and we got a negatively charged oxygen here. Strong base, not resonance stabilized. This oxygen is also negative, not resonance stabilized. If you watch the order of basicity video, you'll discover the attached carbon actually pumps in electrons. It's a orthopair directing group. If this carbon was set on a benzene ring, these carbons are actually supplying electrons to the oxygen, making it more negative and more basic. So this oxygen is actually more basic than sodium hydroxide, which you know to be a strong base. Yeah, so the product of the Grignard is still a strong base. So we add the acid to neutralize it, make it much more stable. And the final product is to the oxygen, add a hydrogen, make it an alcohol. And that's all you have to write. If you want to know what became of the MGBR, well, it reacts 2 times. There's 2 of these bases that actually pull 2 of the hydrogens off and make hydroxide ion. Whoops, not that structure. So the Mg will still be 2+, the Br will be minus, and then there'll be a hydroxide ion and forms this mixed salt, right? The whole compound has a net 0 charge, but it's a mixture of anions. Cool, done. Same deal down here. Sorry, my arrow kind of missed. Let's hit it. Try it one more time. There we go. Grab that H+. And then copy the molecule. Make your alcohol. What degree is this alcohol? Well, can't talk to the oxygen. Talk to its attached carbon. Hey, carbon, how many carbon atoms are you linked to? 2. I'm secondary. Yeah, so is the alcohol. The alcohol is secondary also. How do we get secondary alcohol? Because we didn't use formaldehyde, we used a different aldehyde, benzaldehyde. Cool. Hey, you want to see the mechanism for a ketone? Some of you are like, yeah. Is it going to be on the exam? Could be. Well, all you have to do is change your aldehyde to a ketone. Change your aldehyde to a ketone. Change your aldehyde to a ketone. There you go, we're done. Same exact mechanism. Just going to have the lone pair, bump up the pi bond, keep drawing all the atoms, don't lose them along the way. Attach the new R group, the Grignard reagent carbons, connect them there. And they're there, and then you end up with a tertiary alcohol because you started with a ketone. Sweet. Okay. The ester provides a little bit longer mechanism, but it looks extremely similar. It has all these same steps. We just have to add a little bit more because there's the other oxygen in there. Okay, so how about we start with a, let's back up. Let's put iodide on here. Change it into a Grignard. So you don't have to show the mechanism for forming the Grignard reagent. It's a redox reaction. So we're not going to show that on our test. I might ask you to show the mechanism of reacting a Grignard reagent, this one. And then we're going to do a Grignard reaction with an ester. I don't know, should we just use non-acetone nail polish remover, ethyl acetate? Why not? And we always add acid afterwards. Always, always. Okay, start the same way. My preference is to draw the resonance structure. You don't have to do it. But a lot of our mechanisms begin on a lone pair. So, hey, here's a lone pair on the Grignard too. So maybe that's where my mind goes. Okay, so lone pair, go bump up the pi bond of the ester. So that's the same thing as what it did with the aldehyde or the ketone. Beautiful. So copy everything. Okay, whoops. Here's my ester. So all these atoms show up over here. We just don't put in the double bond because now it moved up on the oxygen as a, well, let's see. The ester has its top oxygen with 2 bonds, 2 lone pairs. And so the pi bond went up there. Now we have 3 lone pairs on oxygen and negative charge. This carbon lost its pi bond. Yeah, so it could connect to the benzene ring. So let's draw the benzene ring. And this carbon, there it is. This carbon used to be attached to magnesium. So that's the point of connection to the ester now. So you connect these 2 together. And I missed. Try again. That's better. Cool. And if that's your intermediate, you're good. So that's nice. 2 arrows. Okay. The wrong thing to do is say, oh yeah, H plus goes on here. And what you'll see then as your product is an alcohol and an ether on the same carbon. We're going to learn in unit 2 that that's unstable. It's not the final product. So once we see unit 2, this will be a reminder, hey, this Grignard reagent reaction is, the mechanism is different than for aldehydes and ketones. What this molecule will now do is say, you know what? I want my double bond back. So the oxygen will drop the lone pair down to restore the double bond. And this carbon says, whoa, 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 I can't make 5 bonds. Someone else has to go. If we're going to make a double bond, the oxygen, this bond, or that bond has to break and go away. Well, the carbon, the single bond on the left side is to a carbon. Carbon-carbon single bonds are really stable. Alkanes are very stable. Way back when we first introduced the alkane functional group last semester, we said, that's a very stable bond. You can basically burn it. You can do free radical halogenation on it and not much else. All the other reagents, leave it alone. It's so stable. This is also a carbon-carbon bond. The bottom bond is also very stable. That's not going to break. But wait, this oxygen is more electronegative than the carbon. It's tugging on these electrons already. It just needs a little encouragement to break those electrons from the carbon completely. So when the lone pair comes down to make a pi bond, to restore the double bond, this bond breaks. And let's scroll to the right so we get some more room. Come on. Let's see if I can keep the whole thing in here. There we go. Okay, so let's follow what happened. It's kind of nice I made these lines bold because they stay there. So let's keep them bold. and then the benzene ring's over here. So I just copy the bottom part of this molecule. This carbon here now is double bonded to the oxygen. And this bond broke, so don't draw it. So now we have the O with this over here. And let's see, going way back to the ester, we have an oxygen with 2 single bonds, so it should have 2 lone pairs. Still has the same 2 lone pairs here. But this bond breaks to form a 3rd lone pair. Now this oxygen is negatively charged. And we actually have a ketone now. Wait, doesn't a ketone react with a Grignard? Sure does. Okay, so what you have to do is remember that if you go in the lab, you don't take your molecular tweezers and grab one Grignard molecule, throw it in the beaker, and grab one ketone molecule. I'm sorry, that's an ester. One ester molecule, and then react, and you're done. No, you put in Avogadro's number, right? Whole mole. So as you mix it up, mix up your Grignard with the ester, some of these find each other right away. The Grignard bumps into the ester, and boom, make the ketone. There's still Grignard reagents floating around saying, hey, where's my ester? Oh, wait, here's a ketone. Let's attack that instead. And that's what happens. So you take in a second Grignard reagent, and now I'll show the second mechanism, right? Second option. You could draw the resonance structure if you want, or we'll take the other option. Just start a curved arrow on this covalent bond. Say, hey, these bonding electrons between carbon and the magnesium, they're going to attack over here. You could come in from the bottom. I kind of like that analogy of bumping up the pi bond, but coming from the side is legal also. And you're going to bump up the pi bond again. Let's draw it over here. Screw this up, give myself a little more room. Okay, so after the second Grignard attacks, well, copy everything here. So let's copy. Right, so there's my ketone, copied over. Where's my double bond? It bumped up onto the oxygen as a 3rd lone pair. It's negatively charged. Where's the Grignard reaction reagent? The benzene ring needs to attach to this carbon. You decide where you want to put it. Do you want to put it on the right-hand side? Draw on your ring right here then and connect. You want to bring it in from the bottom? You can still do that too. And I feel like there's more room down here, so that's what I'm going to do. So this carbon is this carbon of the Grignard, and they're going to connect, that carbon's connecting to where the C double bond O used to be. Okay, now if some of you are saying, well, can't the lone pair drop back down and restore the double bond? Not this time. If you say, well, let's try and do this step again, have the lone pair of the oxygen come down and make the double bond again, maybe the molecule thinks about that. Oxygen says, yeah, maybe I want my double bond back. Well, this is a carbon-carbon, carbon-carbon, carbon-carbon. They're all too stable to break. Doesn't happen. So sorry, oxygen, you're stuck with the lone pair, 3rd lone pair negative charge. You're done. That molecule changed. This one didn't. This one didn't react. So it's still there. So let's copy it here. And now second reaction takes place. In the lab, we watch for all the color changing, the boiling to cease, stir it up. Sometimes you warm it up just to make sure the Grignard reaction's all done. And then when you're confident, yeah, I think it's done now, dump in some dilute acid. And now we have negatively charged oxygens, strong bases. We're going to need more than one hydronium ion, at least one for each negatively charged oxygen. That's a weird curved arrow. We can do better than that. There we go. Okay, so each one gets an H+, and then we're left with, well, let's draw that first molecule. There it is, copied it over, but now the oxygen has its hydrogen. And we have our tertiary alcohol. And then over here, the other piece of the ester, that got kicked out as another alcohol, right? So copy this piece over and add an H to that. And we have the fragment of the ester. We have another alcohol. And this one you do have to include on exams, right? We're supposed to track all the carbons. And there's your mechanism for the Grignard. Yay! Water break. But it's pretty much the same as the ketone and aldehyde reaction. We just have to remember to do it twice. Remember to put in this step to reform a ketone, and then just start the mechanism over. Oh yeah, Grignard's react with ketone, bump up the pi bond, and then the last step of the ketone reaction, quench the base with H+. Cool. So now you know how to do a Grignard reaction, both from a mechanistic point of view and from a predict the product point of view. Such a great versatile reaction. So many things you can do with it. You make tons of molecules. It's not perfect. There's two huge problems you have to watch out for. So remember when we were doing Friedel-Crafts reactions and they had all those limitations? Friedel-Crafts alkylation reactions can do carbocation rearrangements. If the ring is too deactivated, doesn't work, things like that. We have to watch out for those limitations. In Friedel-Crafts reactions, we got two big limitations for Grignard reactions. Okay, there's some logic behind it. So it's not new information. I just need to point out to make you aware some tricky ways these limitations can sneak into homework and exams. Okay, we just said Grignard reagents react with aldehydes, ketones, and esters. They do. So what do you think about this molecule right here? It's a molecule that contains both a Grignard and a ketone. Huh. You can't make that molecule. And again, you're not using molecular tweezers, right? You're gonna have Avogadro's number of these. So if you could, or if you attempted to make this, as soon as you made one, it would attack the other. The Grignard part of one molecule would bump up the pi bond, attack the ketone of the other. It just does not exist. That's a big limitation. I know it. So if you're doing multi-step synthesis, you might think of a way to make a molecule. Ooh, if I put the ketone here and then I can connect it. Ooh, I need more carbons. I'll connect it with, maybe react it with an ester and aldehyde. No, you got the limitation. And you can't create a Grignard reagent that already has an aldehyde, ketone, and ester. Cool. All righty. And then it's not only those three functional group, it's anybody that's C double bond O. So now we're talking carboxylic acids, anhydrides, amides, anybody with C double bond O. You can't have a Grignard reagent and this C double bond O, the carbonyl group, in the same molecule at the same time. They're incompatible. They don't coexist. The nitro group has a pi bond between the nitrogen and the oxygen. So, right? So if we have the nitro group, we usually just write NO2, but the Lewis dot structure has a nitrogen with a positive charge and a double bond oxygen. Grignard, you got this very powerful base, very negatively charged carbon attached to your Grignard reagent. It's going to bump up the pi bond of a nitro group. The sulfonic acid group, right? The SO3H group has a sulfur oxygen bond in it, double bond in it. Two of them, in fact. So these pi bonds can also react. So you can't have a sulfonate group or a nitro group. And then the triple bond between a carbon and nitrogen of the nitrile, nitrogen is more electronegative than carbon. There's a positive charge on this carbon with a pi bond. Yeah, so you can't have any nitriles in your Grignard reagents either. Okay, these are serious limitations. But again, they kind of make sense. If you already know Grignard reagents react with aldehydes, ketones, and esters, C double bond O, make sure your structure of the Grignard does not have a C double bond O. And also make sure it doesn't have the CN triple bond. Cool. Second limitation, we already pointed out Grignard reagents are powerful bases. Don't breathe on them because the water in your breath will react and quench the Grignard reagent. Well, you can't make Grignard reagents that already have acidic hydrogens present. So here's an example, kind of illustrate, well, why not? Suppose I want to Here's a C double bond O. Why don't I just bump up the pi bond? So take these take the Grignard's negatively charged carbon and use those electrons and bump out the pi bond, try and make this intermediate. The problem is, let's draw this, let's draw the resonance structure of this. So the Grignard has a negative charge and a lone pair on that carbon, and we want it to attack the carbon that's slightly positive. The problem is carboxylic acids are acidic. This H plus is also positively charged, and acid-base reactions are so much faster. The lone pair actually goes after the H plus and doesn't even see that slight positive charge on the carbon. So it reacts down here and makes the anion of a carboxylic acid. And then you actually make ethane. Why? Because these two carbons just grabbed the hydrogen and you made this very cheap, not very interesting alkane. So you just ruined the Grignard. Okay, that's a serious limitation. You can't make a Grignard reagent that possesses acidic hydrogens. So carboxylic acids are incompatible with Grignards. Can you make this Grignard? It's way over there on the other side of the benzene ring. But that's benzene sulfonic acid. That is acidic. So nope. This molecule and that one do not exist. Nope, can't make that because that's acidic. What else do you have to worry about? Well, I got a nice little chart I found off the internet. Here you go. We already said carboxylic acids. Ooh, C double bond O, I guess is, sorry, S and two O's kind of show up here, but you might want to put the SO3H group here. If you have an acidic hydrogen, the Grignard will react with that and not do what you're hoping to do, like react with aldehyde, ketone, or ester. It'll react with these hydrogens. Thiols have a hydrogen on the sulfur. That's acidic towards a very powerful Grignard base. Amines and amides that possess a hydrogen on nitrogen, yeah, that's also acidic towards the Grignard. And alcohols, yeah, the hydrogen on an alcohol going to be pulled off by the Grignard reagent. Serious limitations. You cannot have any of these 4 or 5. Include that one. Any of these 5 functional groups cannot be on your Grignard reagent. They're incompatible. And then we already mentioned all the double bond O's. Yeah, nitrogen double bond O and the triple bond between carbon and nitrogen. These, okay, those some serious limitations. Your Grignard reagent cannot possess any of these on the Grignard reagent. It doesn't work. You can't make the Grignard reagent with these functional groups. They are incompatible. Ooh, I think that's the end of our video. One more to go for Unit 1. See you in that one.